So, here is, let me put it this way. Let me try to draw some perspective on the context of the problem from the standpoint of what you might have already learned in your courses. So, let's put it this way. So, if you come from data science background, you might start with the problem. So, what is this about? Actually, it is about solving problems, certain problems. Okay. And in reinforcement learning, there are specific problems. So we will now kind of try to draw an analogy and difference between a problem, for example, a typical problem in machine learning, in data science, and in reinforcement learning. Okay. So in another perspective, say. You might have something like minimize some loss that depends on the model and on data, where data is a sample, for example, from some joint true distribution. In machine learning, what you have, most of that, there's a data set, you draw samples from that data set, let's say in the form of mini batches, then you state the loss, you choose a model, that's for example a neural network, okay, and we think we need some statistic that could be, for example, just the mean. Yeah, let's try it for you. Put some loss, whatever, mean square error, cross entropy, what have you. And then you just then the game starts, and you try to find parameters that fit that model the data best, like hopefully, you know, without overfitting and underfitting and biases and whatnot. This picture, you might see it dynamically, right? So, what is the typical procedure? The typical procedure would be something like, you know, you got WI plus 1, assign WI minus, for example, learning rate, and then gradient of loss. Mini batch. So, when we say something is dynamical, we mean evolution in time. Time is something that should be understood in the most general way, abstract. It doesn't even have to be like literally time that you see on the watch. Rather, it's like a certain dimension that the game exists in, where you can define such a notion as a step or iteration, epoch, whatever. Okay? So here, the data, the mini batches, for example, they are sampled from some underlying population. For example, you might have a huge data set and then you draw separate mini batches from the data set, whereby each should be sampled independently from the others, right? And identical to avoid biases and whatnot. So, if you come from, let's say, control engineering perspective, which is actually which is adjacent to reinforcement learning, you might have a problem like, for example, you have state, next equals some function, state current, and current control. Something like that, and the goal might be, let's say, minimize some objective that depends on the state or sequence of the states subject to control, or maybe you want something like that. I want state to go to some starred state. To denote some target state, okay? This is, if you, for example, if you attended a control course, okay? Now, the difference in reinforcement learning to this kind of perspective would be that the data that are sampled, they are not sampled independently. Rather, they are generated by an underlying process, okay, that can be summarized in this notion of environment. Now, if there is an environment, there needs to be something else. If the data are generated from the environment, then what we are doing, the decisions that we are taking, this is our decisions. That's the decision. You decide what value of the parameters to take. Okay, you do it by stochastic gradient descent, for example, add and what have you. Here, the decision is the control. Control is the decision. Okay? In all cases, that's the decision variable, and that decision is usually put into the notion that is called an agent. So there's like an agent, and then there's environment. That kind of word choice might be not optimal, but it's just the convention. Because just think of the associations that you get when you just hear that word. Environment. Environment it's like a surround. Okay. For example, when we take a robot that navigates somewhere in some room with other items, persons, whatnot, you might tend to call that kind of room where it operates environment. But in reinforcement learning, for example, if you control a robot, then environment collectively would be everything besides the the entity that takes decisions. See? And if you associate with the decision control, which in case of a robot, I guess everybody could draw an association with control of a robot. That could be torques, turning angles, maybe, whatever. Then the robot itself is a mechanism, okay, with electronics in it, should by definition be also like a part of the environment. And that's a little confusing. But that's just the way the terminology goes. So now, again, difference is that data are now generated by an environment. Now, so the environment it is something, it is an entity. At the end of the day, we gotta put everything into some formal language, right? So the environment has gotta be something that is expressed mathematically. Mathematically, it is most of the time it is a Markov chain. So what is a Markov chain? Markov chain is a process that evolves in time, step to step, that has a certain property, which is called state. And that state evolves according to certain law. That law is called transition law, or state transition law. Now, one of the most difficult things to understand here, especially that when it comes to concrete applications, where you really need to figure what state is, what is state, and how you put it down, how you put it mathematically. Okay? Simplest scenario, the simplest scenario is state to be a vector. A vector is a Cartesian of numbers. Okay? Could be of arbitrary dimension, but it's just we characterize something about the process. Markov chain could be a mathematical object that represents some physical process, robot movement, a poker game, a finance market, some stock market. So that we formalize as a Markov chain, Markov named after mathematician Markov, who studied these things, contributed enormously to probability theory. So Markov property, in simple terms, means that state in its history, right? State evolves in time, hence it must have some history, right? And every next step is governed by what I said, state transition law. And Markov specifically tells us that the state at each instant in time, okay, depends on the previous step, but not on the whole history. So it's easy to think, for example, of a mobile robot. If at let's say at some point, at some time is, robot is there, okay? Then, where the robot will be the very next point in time depends just on two things. Where it was in the current point in time, and what decision it took, what control of it. It decided to turn, it decided to drive. So there, that next pulse depends on the control that was taken and the current pulse, current. It doesn't matter how the robot got there, how we drove, all of that doesn't matter, okay? What only matters is where it is now and what action we take. So, here's the notation for the things that I've just described. It's not something to be underestimated. Clean notation is one of the keys to success. In particular, in your mini projects, whatever the job you do, notation. If notation is garbage, you will struggle, your teammates will struggle, you will struggle to communicate, you will struggle to transfer knowledge and information about your problem, your project, your solution ways, etc. Notation should stay consistent. When it was introduced, it should stay. If you use that letter to denote this or that thing, it should stay consistently throughout the discussion. So, in Markov chain, we have a state. State is denoted by letter S. So, then we assign a subscript to the state to stress at what point in time we consider this state. For time, again, take it as meaning. It could physically, it could be anything. It could be some step in a turn-based game. It doesn't have to be like literally the physical flow of time. So we use the notation T. Okay. So in the Markov chain, every next state, for the next state, we will just add 1 to the time step. T plus 1. And that thing should be sent, that notation needs to be sent from. Okay? In terms of probability theory. Some transition law, which in our materials, most of the time, that will be what's called probability density function, or PDF for short. Probability density function could be continuous or could be discrete. Okay? We'll use a small letter p for that. Okay? For a generic argument, we'll use just a bullet like this. Then, for the conditions, we'll use the following notation. A vertical dash, and after the vertical dash, there come the conditions. And Markov property specifically dictates that those conditions should be just the current state and the current decision. Now, the current state is, of course, S T. Okay? If T plus 1 is the next step, then T is the current state. And a decision in reinforcement learning is also called action, and is denoted accordingly by letter A. Now you see that I drew that letter A as a capital letter. This is not without reason. In fact, these two letters are also capital letters. Why? Because most of the time, capital letters will refer to random variables, and small letters will refer to concrete values as numbers, vectors, tensors, whatever, something tangible. Or in language of probability theory, also called realizations. So, this is state transition. If the PDF is discrete, it's also called probability mass function. Now, there is, just for your awareness, there is more abstract objects behind this setting called probability measure, probability distribution, that would explicitly rely on sample space, but we will mostly work with induced measures that we can evaluate on target spaces. So let me just remind you that there's a random variable. In general, it is a function from sample space into some target space. Most of the time, for us, the target space is just some Euclidean space, some n dimension. Okay? This is the target space. And although you might consider like a probability measure, okay, that might be evaluated on sets in the sigma algebra or that sample space omega, for example, omega 1 is in that sample space, something like that, okay? We will most of the time, probably even never, use these kind of things. In our setting, we will mostly use induced measures, the probability density. And the probability density, as you can tell from here, it takes as an argument, okay, just that number of vector. So a PDF would then map from Rn, from the target space, directly into, well, in general, into R, non-negative numbers. Okay, if we're dealing with continuous random variables, then probability density as a function can take any non-negative. If we are dealing with discrete probability densities, alternative term for discrete probability density is just probability mass function. It directly assigns probabilities to concrete target outcomes of that random variable. So if for example, if this is a roll of dice, okay, then you can say that target values of that random variable are the numbers on the dice showing up, from 1 through 6. And the probability mass function would assign to all these numbers from 1 to 6 a certain probability, so that all add up to 1. So, let's recap. So what we see here is a law described by state transition PDF that is conditioned on the current state and action, and that gives probability density for future state, one step ahead. So let's consider an example. Shall we? Check. This.
Looks like there's an error or something.
Okay, so here's an example. A mobile robot on a plane. Physically, we know that the equations of motion of a mobile robot, they go like this, right? X is the x coordinate, y is the y coordinate, and the bar theta is the turn angle. Now, first, it's simple to figure action or control. In case of a kinematic robot, it's just the translational velocity and angular velocity. It's v and omega coordinate. Now, the state, something is not, like God-given. State, we have to define what state is. Okay? In our assembly, there's no universal criteria. It's just, the criterion is just practical use. What would give us good service as a state? So, for the robots, in kind of everyday life terms, probably not so difficult to figure. If I freeze the time, what should I take as the state? And if I let the time go, that state that I define, of course, at the next point in time, right, it should be something consistent. And eventually I should get to that mark of chain forward. So here, it's kind of self-evident that, yeah, we should take something that describes the position of that robot on the plane, and because robot, right, it's a kinematic system, we also need to take into account the turning angle. So probably those are good enough. Just the two coordinates and the angle. Fine. Now, these are differential equations. Most of the time in reinforcement learning, we don't want to deal with differential equations. We want just to operate in discrete time with discrete moments, steps. Step 1, 2, 3, and so on. But here we are talking about native physical application, okay, physical process, which is the motion of the robot on the plane. And that process is just as all other physical processes, is continuous in time. So that's the catch. Physically it is continuous, but we want to consider it in discrete time, just for convenience. So we have to do some job before we even get to a proper set. The job is just to discretize the differential equations. And to put them into some convenient eventually numerical integration setting. The simplest is just Euler forward method. Okay? For that, I don't go into details of that. You just take the right hand side of this, compute the Jacobian, and so that you can put everything into a form like that. Some matrix, Jacobian matrix, times the state vector plus another matrix times the action vector. That's how we first get into the discrete time. Okay, step number one. Step number two. Of course, when we transition from continuous time into discrete time, we will, of course, lose some information about that process. Not only that, in reality, like what's written here is it's a simplified picture. Those are just purified 3 simple equations which reflect the reality to some extent, but of course not completely. Because there's, I don't know, could be some friction, some small malfunction maybe the drives and whatever. So, now practically, it's impossible to describe all that in detail, or otherwise you could end up with hundreds of differential equations. You could go to quantum level, whatever. Of course you don't do that. So that's why that uncertainty, okay, that factors that we did not account for, they are packed into a smaller collective mathematical object that is in charge of those uncertainties, so to speak. So there is approaches to that could be, for example, packed into some function that evolves at times something, or maybe just like some residual variable, whatever. But most conveniently, it is done via packing everything into the probability theory set. We would just say like, okay, now our state, although in reality, there could be like, maybe that system is like literally deterministic. You never know. Yeah, just to say that, in the end, it's just a quantum system, some other. You could very well also describe quantum formula as purely deterministic. But it's a side question. The thing is that you don't care. For you, probability theory is just a handy formalism. Okay? Disregarding the interpretation. Like you interpret it frequentistically, or intuitionistically, like that you believe that with so or so degree of credibility, whatever probability, that product could be here and there or there, if I apply that action. We just put that aside. So, okay, we don't talk about concrete states anymore when we predict, when we determine the next state before it happens. But rather we just put the probability, a PDF, we just throw a PDF on top. And that PDF hopefully should account for all the uncertainties that are there. In particular, that uncertainty is our unmodeled dynamics that we discarded. What is that letter? Anyone know? What is that calligraphic N? Of course, it's just a good old normal PDF. So this is the normal PDF. and that's of course, that's the mean, and that's some covariance measures. In simplest cases, just a diagonal matrix with answers corresponding to squares of standard deviation. So, and that's it. So this thing here is a legit Markov chain that we built off of that physical process that we started with. Okay, so just robot movement. Right. So, now, getting back. So we have our process. So now the scene is already populated. Now there's quite enough. There's the Markov chain, and here you see one of the key differences. If you want to control this environment, to throw some decisions on it through this channel that is called action, right? And if you compare that Markov chain formalism to the one that you have in data science, you see that one of the immediate differences, as long as you base, for example, those states, is that's the information that you perceive. What's there else? Just a state. Now that state, unlike this data sample, it's not sampled like independently, but it's sampled from here. According to some law, and that makes things extremely interesting. Especially when we come to one of the most prominent methodologies of reinforcement learning that's called policy gradient. Something that you wouldn't see just as such in machine learning, or even control. That, not temporal, that I would call the major distinct property for reinforcement, the major merit of reinforcement learning is policy gradient. Now, if you come from this perspective, control, that's easier for you to just draw the connection. Not much has changed. There's the next state, maybe you used to this kind of definite function, deterministic, just ordinary function, and deterministic law that describes how state evolves, and there's no random variables, and folks from advanced control course should probably recall they didn't even need that discrete time so much. They could just, get along with differential equations. Because, differential equations, as much as you might not like them, they have their certain beauty and many derivations in the realm of differential equations. They are, especially when it comes to control, they are nice and pleasant and not so much discretized. But the thing is that you try to keep things probabilistic and still continuous time, and you get to stochastic differential equations, which are just so nasty. You don't want to touch this. Okay. But, so, Markov chain is there. Where's the problem? What's the problem? Well, so let's enrich our context. So we have Markov chain. And to get to a problem, right, we need to define the goal, so to speak, There may be some metric. So how do we even quantify how good are we at solving the problem? So for that basic metric, in reinforcement learning we put reward. Reward is again something some of you might find this term a little confusing. Like we talk about the robots, hard to tell what is its reward. It's not getting nothing from solving the task, all right? We don't pay or something, okay? But the terminology is just the way it is. Sometimes, although it's called cost, which is also some might be better, some might not. Okay, but let's say it's a discussion, it's a separate discussion. So anyway, we put here reward. So reward, in general, it's also random variable, a scale of one, so just a number, could be negative, could be positive. And it is also sampled, generally speaking, it is sampled from its own PDF. So in general, you could write something like, to distinguish that transition from the previous, let's put R, capital R on the source. And that should be conditioned on the current state and current action. So what we are doing here is that through that reward, we are given a judgment to the action taken while being in that state. So, like answering the question, is it good what you're doing in that state? Should you do maybe this or that action? Or should you take this or that decision? Now, at some point in this course, I will hit you. By the way, please raise your hands if there's are there any math guys who would like math, like to dive into. Very, very good to have you here. I will pay attention to you. At some point, for example, you will decide. Maybe I want to dive somewhat deeper into policy gradient. Where does this formula come? What is the correct formula in the end? And then you look at canonical papers, and definitely you won't understand it. You won't be alone. In fact, not so long time ago, I just, wanted to kind of complete some gaps in my own understanding of policy gradients, and I studied through, Schuman's papers, translation policy communication. And then of course, here there's type there, this thing is not so well explained. Then you see something like, oh, for continuous case, what is mentioned, state, think of the law. What do you think? If the coordinates and the turn and end constitute the state of that world, would you say that the state is a three-dimensional vector, right? Three-dimensional, where each entry is a real number? You agree? Right? So most of the time, those physical variables are continuous. We leave argument in a continuous form. Okay? Put details, physical details aside. So continuous, length is continuous, coordinate is continuous, torque is continuous, force is continuous, everything is continuous. Right? Right. But it just so happens, also is the case in that textbook by Sutton Barton, the Arial partitions, they go further than just say the time is discrete. Okay, we can consider like everything at discrete points in time. Fine, okay. I mean, probably that microcontroller that you put in your robot can even operate in continuous time. It has some minimal sampling period. It cannot just generate actions infinitesimally fast, right? That's understandable. But what you control the state, that's for sure continuous. Or should you consider it like, moving on a grid, or turn it just by some angle. But the matter of fact is, Arial partitioners, they go beyond that and they put state space, the realm where the state exists. It's denoted like that. So as now small f is quantum vector, it lives in this kind of letter S. If you were using LaTeX, it's math BD FS. Boldface S. So this is the state space. So they put the state space to be a finite set. Finite set. For example, just a table. Finite table of designated states. And actions also. And also actions. This is what we will concentrate in tabular reinforcement learning. In your first mini projects, you will deal with finite state and action spaces. Probably most of you are going to use something like a GPU network, and that means normally, state space to be at least discrete, or at least action space to be discrete. And you go, so going back to you guys, you go through that, and you see something on the footnote saying, oh, all the theory that we present here extends to the case of continuous state and action spaces. Straightforwardly substituting sums for integrals. And then there's two ways how that situation works. Either you say, okay, well, fine, I'll just get along, I'll believe it. Or option number two, you will take a deep look into that, you will try to think about this, okay, but how exactly, and then at some point you will be like, just total butthurt rage. And you'll just realize that not even once ain't gonna work like this. It simply, it doesn't work. And you will have to figure out yourself. And that's a long time ago I consulted experts forum on that. And the answer in the end was precisely like that. Just, they didn't give this exposition. No, nobody did that. It's just you're just using it in like shut up and code. Not maybe not even code. Just shut up and tune. Oh, just adjust the learning rate. It's a universal advice, right? So for you guys, I will roll out at some point later. I will roll out a collab where I did my exposition of policy gradient theory and trust region policy gradient theory in particular. where I actually did transfer those goddamn sums into intervals. And oh boy, it wasn't straightforward. Right? So, my message is that think of this critically, okay? Not everything is so just easily extendable to continuous state connection spaces. And you might end up in a situation where you are knocking at an open door, trying to fiddle around with that learning rate. Sometimes, fortunately or unfortunately, the problem is deeper, and you have to dive in, like really like, oh, am I really even like having Markov property here in the first place? Like some tricky situations like a snake game. You know the snake game? Why not? And that should distinguish, and that should differentiate you as students who got higher education at school tech, for example, from just some amateur folks who just play around with baselines and ChatGPT and in parallel, you know, look at some YouTube videos and blogs, whatever is not yet blog. That's the difference. Okay? So hopefully you eventually get some, you know, degree of critical thinking. So in my notes, I actually used this, but in this course I want to simplify. So I will simplify. I will not consider reward as a random variable. I'll keep it simple. I'll just assume that there is just a reward function, or what's also called reward rate. It's just a function that maps from state space and action space. So by analogy, this thing is just action space into numbers. So U are some. So R, S, and A is basically like, let's say, T is simply the immediate. That's the reward that you take, you get when you take this action, right? While you are in this state. So, and again, also an example of a reward function. Let's see. So you see here, it says coast. It's not a big deal. Just throw a minus at it. So you would write something like RT equals minus, and then there is, for example, Euclidean distance between, let's say you're doing like a robot parking problem. So you want to drive your robot into target coordinates, and you also want to hit target orientation. Right? So it could be understood as a parking problem. So S star to be like, you know, target state, something like that. For example, if you care about action effort, add this kind of term. If you don't, just leave it behind. But what we see here is that kind of reward function makes sense. That the highest reward, which is evidently 0, is got precisely when we are in the target state. So that's what happens. Everything else will get us larger negative rewards, right? So then here constitutes another key ingredient of our real problem, and we are just a couple of steps of actually formulating the problem. So let's think about this. If I am to drive the robot to the target position, to the target post, is it just enough to consider reward at this current step? Would that really get me, just to the state that I want? For example, if I were really to take something like that, whereby the second term is like control effort, the less action you take, the less punishment, right? But in that case, I mean, just okay, take action 0 and that's it, like, because you don't have any influence on the current state. You only have, by your actions, you only have influence on the next, on the subsequent states. So how should we put that into the play? How can we account for the whole process of solving the task, of getting to the goal? I need to take account of the future states. So, of course, one immediate way of doing that, of taking that account, is to evaluate reward at the next stage point. Take the reward at the next stage. But developing that kind of logic, you might get to the conclusion, why not to take all of them? All of the states. Let's take all of them. Evaluate all of them. Okay? One of the simplest ways to do that is just to take a sum. Take a sum of those. What we will sum with respect to time. We started at point at time step 0, and we ended at some time step tau minus 1. So that all in all, we have tau time steps. And we take all of these guys. But listen, what is the state as such? That object, it was a random variable, right? It was a random variable. So I'm forced to write this in capital letter. Just as I should in case of an action. If that action, we will get to that action in a moment. Okay. But so far, let's keep it as general as possible. Okay. Action also random. So we sum this up. Okay, good. But if you just look at this plainly, this is of course a random variable, right? R is just an ordinary function, but the arguments of it are random variables. So, but you cannot optimize a random variable. That's next to impossible. And what you do in real life, if you maximize profits, maybe portfolio, stock market. In fact, you are maximizing some statistic. That's the same thing as here. You're not minimizing the loss, you're minimizing a statistic. That statistic here is the expected value. Same thing here. Take the expectation value. Square brackets to denote that, well, normally expectation value is an operator, right? Operator is like a generalization of a function that takes as arguments, takes other functions. This random variable is a function. That's why we distinguish square brackets and just normal brackets. So, well, it's already starting to look more or less tractable. And if now we need to add an anything. So if you like mathematical cleanness, you should specify the PDFs, the distributions, right? The PDFs for the random variables involved. Okay? If you are into engineering thinking, I have an interpretation for you as well. And I will tell you that interpretation. It's my, like, you may find this comforting or maybe not so comforting. It's up to you. But first of all, for the formal folks here, let's write down what are the distributions. So at least we should put here distributions, the PDFs for the states. So then PDFs for the states are our state transition laws, right? Sometimes, like in literature, all of that is being packed into something like this. This is an abuse of notation. But let me show here. So, if you do not like math format as much, and you just like coding and engineering and stuff like that, and you see this nasty symbols. Keep that so that the screen doesn't go off. So you see that symbol. Read that E, what it says. It says experiment. So, what I mean by that, for you, okay? You are coded, you are doing an experiment. So for example, this is the robot parking problem, for example. And somebody asks you, okay, how do you even evaluate this? General advice, if you feel uncomfortable with some math, try to think of this the following way. How would I calculate this? How would I code this? How would I put this into code? Okay? So, in this case here, you are asking me to somehow calculate this statistic, which is the mean or average or expected value of that random variable. Now I know that random variable is a nasty thing. It's some function, on some peculiar sample space that hell knows what even is. But one thing I know for sure, that when I do my experiment, when I run the robot, I know goddamn well that it was in that state, then it went to that state, I took that action, so on and so forth. Those were very concrete, tangible numbers that I can protocol, I can code, very concrete realization. That's why they're called realization. Because these things, random variables and expectation values, they don't exist in reality. They are transcendental. That's the thing. You look at it, you get confused. But when you see that, for you as engineers, that would mean a certain recipe, a certain instruction, how to act. Instruction is, okay, if I see that, I will have to repeat the experiment. I read it once, twice, Either 10 times, 20 times. Okay? For each of the times, each of these runs, or what's also called the reinforcement or an episode, I got this. I got a realization of it. So, what I do with those, I just sum them up and divide by the number of the runs, right? The episodes.